we defined the concept of a probability density function for continuous random variables. Let's quickly go over that. So a random variable x is continuous if and only if there's a non-negative function, fx of x, okay, called the probability density function, such that you can find the probability that x takes values in a region B, okay, by integrating over B the density function. Okay, so the density is like probability per unit length or probability per unit area, depending on, of course, what the dimensions of x you are integrating over is. And only fx of x is not a probability itself. Only when you integrate it, you find a probability. Okay? So it describes how concentrated the probability is at that point x. Okay? Now, so the probability that x is in between a and b can be found by integrating from a to b the density. Now, PDF is non-negative. And when you integrate the PDF from negative to positive infinity, you should get 1. Why? Because that would be the probability that x takes values from negative to positive infinity, which should be an event with probability 1, according to the way we defined random variables. Okay? Now, for small delta, you can think of the probability of x being between x and x plus delta, which is the integral from x to x plus delta of the density, roughly as fx of x times delta. Okay, so that gives you an intuition of, another intuition, if you will, of what density means. Okay, so fx is like a probability mass per unit length near that point x. Okay, now fx of x, the density, PDF, may be larger than 1. Okay, so unlike probabilities, densities can take values larger than 1. As we saw in this example, it went up to 3 in this example. It can even take infinite values at some regions. Okay, so this was an example where the example with a typo, which is still not fixed here, where the random variable took negative values. I'm sorry, infinite values. The PMF took infinite values. Okay. Now, we also saw some generic important continuous PDFs. The first one was the uniform, the continuous uniform density. Random variable is x is uniform between a and b if its density, PDF, is constant between a to b. Okay, it's a constant level in that interval from a to b, and it's a single interval. So since it has to be constant and it has to integrate to 1, that level should be 1 over b minus a. Okay? Today, we will compute the expectation and variance of this random variable. The next one we looked at was the exponential. I'm sorry, next one is, oh yes, it is the exponential. Let me see if I skipped it. Oh, the next one was Gaussian. The Gaussian PDF exists from negative infinity to positive infinity, and it's given by this function. This function is characterized by 2 parameters. Okay? One of the parameters is sigma squared, which is the variance of the random variable x. The other parameter is mu, which is the expectation of the random variable. If you look at the plot, it looks like a bell-shaped curve. In this figure, it looks like it's going to 0. Actually, the tails are extending to infinity. They are small, but they are extending to infinity. Okay? This particular example has mu of 0, the mean or the center of gravity of the distribution, is at 0. Okay. And so it's just an example. The variance controls how spread out this curve is. Okay? And the final example of a continuous random variable that we studied last time was the exponential. The exponential is one-sided. Okay? So it exists only in the in the right half, right-hand side of the origin. Okay, fx of x is equal to lambda e to the minus lambda x when x is positive and 0 otherwise. So this is used often to model the lifetime of something. Okay, that a lifetime is usually positive. Okay, and it may decay fast. Lambda controls how fast this density decays. In the example, we're showing lambda equals 2 and lambda equals 0.5. Okay? Lambda equals 0.5 is this dashed curve here. It starts at 0.5 and decays slowly, whereas the lambda equals 2 curve starts higher and decays faster. Okay? So this was the summary of last time. The topic for today is expectation, the first topic for today. Now, we've already done the core of the work here actually, because when we studied discrete random variables, we already covered the concepts of expectation, variance, second moment, etc. So this will not be very hard because it's just an extension to the continuous case. What happens is instead of a summation, we have an integral. Okay. Does everybody have the handouts for today? Okay, great. So let's go on with the definition of expectation. When we have a continuous random variable x with PDF fx of x, the expectation of x is defined as the integral from negative infinity to positive infinity x times fx of x dx, whenever the integral converges. For some continuous distributions, this integral may not converge. Okay? In that case, we just say that the random variable does not have a well-defined expectation. Okay? Now, let's see if we can show, well, the first thing is nothing, there's nothing to show here. Just like in the discrete case, E of x, the expected value of x, is the center of gravity of the PDF. Remember, the expectation was the center of gravity of the PMF in the discrete case. Here, again, it's the center of gravity of the PDF. The expected value of g of x. Okay? The expected value of g of x, a function of x, just like in the discrete case, is found by integrating g of x times the density dx, x from negative infinity to positive infinity. Okay? Remember, in the discrete case, we did this with a summation. Okay, so let's remember discrete case. Discrete case. Expected value of g of x, where x is a discrete random variable, is summation g of x, px of x, where px of x was the PMF. Okay, so the same thing follows for this case too. Okay. Variance of x. How do we find the variance of x? Variance, well, the definition of variance does not change. What is the definition of variance? Expected value of x minus expected x squared, right? In other words, the expected value of x squared minus expected x squared. Well, when going from here to here, I actually use linearity. Okay? This is a definition, and by linearity, I am able to show that it's identical to this one. But have we shown linearity in the continuous case yet? Not really, although it's obvious. So let's show that in the continuous case, for continuous random variables, expectation is linear. How do we show that? The expected value of ax plus b, let's say. Expected value of ax plus b. What is this? This is the integral ax plus b fx of x dx from negative to positive infinity. But integration is linear. Therefore, this integral breaks down into this summation. What is the value of the first term? This is the expectation of x. So this is a times the expectation of x. And what is the second term? It's b times the integral of fx of x over the whole real line, which is 1. Okay, so that's what b. So expectation continues to be linear. In fact, all the properties from the discrete case follow intuitively to the continuous case with densities. All right, so now that we know, we are sure that the variance is equal to the expectation of x squared, which is the second moment. Remember, this is called the second moment, minus the square of the first moment. Okay, we can write this down as an integral, right? Integral, what is this integral, please? This. Who's talking? but the first one.
X squared.
Uh-huh.
Times
fx of x dx. Negative infinity to positive infinity, minus the square of x fx of x dx minus infinity to infinity. Okay, so this is how you would compute the variance for a continuous random variable x. First, compute the second moment, okay, the expectation of x squared. Subtract from that the square of the expectation. Any questions? All right, so then let's see. We already saw that variance is not linear in general. Okay? So let's see what happens when we want to compute the variance of ax plus b. Variance of ax plus b. Well, this is the expected value of ax plus b squared minus the expectation of ax plus b, which is, you can easily show, this is a, excuse me? Squared. Oh, sorry. You can easily show that this evaluates to be a squared times the variance of x. We really did this for the discrete case. This is just a reminder, alerting you that it follows in the continuous case as well. But show this as exercise, please. Okay. All right. So these are really nothing new. Let's continue to compute the expectations of the three, or maybe actually the two distributions that we defined earlier. Let's start with the uniform. Okay. So here's the example. X is uniform, continuous and uniform between the real numbers a and b. Okay? Let's find the expectation of x. Okay, so let's first see what kind of function the PDF is. Let this be a and this be b. A and b don't have to be positive, of course. I mean, they can both be negative, or one is positive and one is negative, as long as the density is continuous in between the points a and b. Okay? By the way, densities do not always have to be continuous. Okay? Continuous random variable means it has a density. A random variable is continuous if it has a density function. A density function is not necessarily continuous. But in this example, it is. So as it's the same case in the exponential. Okay, so let's see. This is fx of x as a function of x. What is the level? What is the value? 1 over b minus a, right. So the expectation of x is integral x times fx of x, which is integral from a to b x 1 over b minus a dx, which is what? B squared minus a squared over 2b minus a, which is a plus b over 2. Is this surprising? Not at all. Why? Because we were expecting the expectation to be at the center of gravity of the distribution, in this case by complete symmetry. The center of gravity is at a plus b over 2. Okay? Very easy. So how about the variance? Variance of x. So before we compute this, what do you expect the variance to be a function of? For example, if I add a number to a and b, okay, so I shift this PDF this way, to the right, or to the left. The variance should not change, right? So what do you think the variance should be a function of? On the other hand, also think, how many parameters does this have, the uniform distribution? Just 2 parameters. Okay? It can depend on only a and b. There's nothing else that it can depend on. But it doesn't seem to depend on the absolute values of a and b, because if you shift this by keeping the distance constant, the variance should not really change intuitively. So what do you think the variance depends on? The difference, b minus a. Right, so let's see. Let's see if we get something that's in line with our intuition. Also, after we do this computation, this intuition can let us test our result, okay? So, what am I going to do? First, I need to compute the expectation of x squared, which is the second moment. Then I need to subtract this from it, a plus b over 2 squared. So, expected value of x squared is integral of x squared 1 over b minus a dx from a to b, which is b cubed minus a cubed over 3b minus a. Well, b cubed minus a cubed factorizes into b minus a times b squared plus ab plus a squared. Okay, so let's subtract these. B squared plus ab minus a squared over 3 minus a squared plus 2ab plus b squared over 4. What do we get? We get b squared plus 4ab minus 6ab, which is minus 2ab, okay, plus minus 4a squared minus 3, oh, there's a plus here, okay, plus 4a squared minus 3a squared, which is a squared over 12, which is what? B minus a squared over 12. So, does it make sense according to our intuition? Yes. It is a function of the difference of b and a. Okay? And it also makes sense that it's the square of the difference, not the difference itself, because think about it. When you take the square root of the variance, what do you find? You find the standard deviation. The standard deviation has the same units as the random variable itself. Okay? So the variance should have the square of the units. So it makes sense that it's b minus a squared. Okay, so now we know the expectation and the variance of the continuous uniform. Let's find the expectation and variance of the exponential. In this one, the integrals won't be as nice. So, let's see. X is exponential with parameter. How many parameters does the exponential have? 1. That's lambda. Now, when x is exponential with lambda, the expected value of x is integral x times fx of x. What is the density? Lambda times e to the minus lambda x. Oops. Dx, and the density is only non-zero from 0 to infinity. Okay, so we need to integrate lambda times integral from 0 to infinity x e to the minus lambda x dx. We can do integration by parts, right? Let's quickly do this. Now, what do? U is x, du is dx, and dv is e to the minus lambda x dx. So v is minus 1 over lambda e to the minus lambda x. Okay, so we need to do uv minus dvu. Okay, uv is minus x over lambda e to the minus lambda x minus v du. 1 over lambda e to the minus lambda x dx from 0 to infinity. Okay, so that's the integral we have. So let's compute this first part from infinity to 0. At infinity, what happens when you multiply x with e to the negative x and take x to infinity? This is a polynomial term that increases with x. This is an exponential term that decays with x. The exponential decays much faster than any polynomial for any power of x here. So this term at infinity is 0 whenever lambda is positive. Okay? So this is 0 at infinity, and what happens at 0? At 0 it's 0 because of this term. Okay, so it's 0 overall. Okay, plus, maybe let's not write that 0 anyway. Let's do this integral. What is that integral? It's negative 1 over lambda squared e to the minus lambda x from 0 to infinity. And that gives us, again at infinity, because of the negative lambda term, this is 0, and at 0 it is equal to negative 1 over lambda squared, which gives us 1 over lambda squared. Okay, so we get 1 over lambda. Okay, so what did we find? We found the expectation of the exponential. Let's see if this makes intuitive sense. Okay, let's remember our exponential fx of x. It starts at lambda and decays. Okay. The expectation, which is the center of gravity, turns out to be 1 over lambda. Does that make sense? It decreases with lambda. So as lambda increases, what's going on? The density is becoming more and more concentrated around 0. Okay? And the expectation, which is the center of gravity, shifts towards 0, which makes sense. Okay? So this is quite intuitive. Okay? Let's find the variance then. The variance of x is, remember, expected x squared minus 1 over lambda squared. So we need to find the second moment in order to find the variance. Second moment, that's the integral from 0 to infinity, x squared times lambda e to the minus lambda x dx. Okay? So we need to, again, integrate by parts, right? So it's lambda times, well, this time it's x squared times 1 over lambda e to the minus lambda x, negative, plus integral from 0 to infinity, x 1 over lambda, let's see, du is 2x dx, right? 2x integral 1 over lambda e to the minus lambda x dx. This term from 0 to infinity, at infinity it's 0, at 0 it's 0, so this is gone. Okay? What do we do about this term? This is simply twice the integral x over lambda e to the minus lambda x dx, which we just did here. Remember, we just did this, and we found the result to be 1. No, we found the result to be 1 over lambda squared. Okay? So this is, it seems, 1 over lambda cubed times 2. Why? Because this is 1 over lambda times x e to the minus lambda x integrated from 0 to infinity. So it's 1 over lambda times 1 over lambda squared, 1 over lambda cubed. So what do we get in the end? 2 over lambda squared. What is this? This is the second moment of the exponential. Okay? The second moment also decays with lambda, which again is aligned with our intuition. So what is the variance then? Variance of x is 2 over lambda squared minus 1 over lambda squared, which is 1 over lambda squared. Nice. Why? For two reasons. First of all, it is simply in terms of the parameter lambda. Okay, just like expectation, this decreases with lambda. Also, this has units which is square of the units of lambda, which also makes sense. Okay. So we found the expectation of and the variance of the exponential. If you maybe want to repeat these at home, this could give you useful sort of exercise for computing the means and second moments of continuous distributions. Let's see, what's next? What's next is another very important definition. So far we've defined a PMF, we've defined a PDF. The next definition is a CDF. The PMF exists for discrete random variables. Okay. The PDF is defined for continuous random variables, but the CDF is defined for all random variables. Okay. This is a new topic and it will need our attention, so I suggest we give a short break and continue after the break.